some fundamentals of the electrochemistry. So here we will start from the basic concept. So first we will discuss about the electrical units. First one is ampere. It is the unit of current. You know, ampere is the unit of current and it is abbreviated as A. And again, 1 ampere is equals to direct current which when passed through a silver nitrate solution under the certain specified condition, that means that the amount of the current passed through the silver nitrate current solution to deposit silver at a rate of 0.001118 gram per second. So that is known as 1 ampere. So it is abbreviated as A. So that is the ampere is the unit of current. Now coming to the next one is ohm. Ohm, that is the unit of electrical resistance, and the definition of ohm is the resistance offered by uniform column of a mercury of 106.3 centimeter long with a mass of 13.4521 gram with a direct current at a temperature of 0 degree Celsius, that is equals to 1 ohm. But here you should know that it is the unit of electrical resistance. Similarly, ampere is the unit of current. Now coming to the volt. So the unit of EMF or electromotive force and potential difference are called volt. So the unit volt is derived from the unit of current and resistance via Ohm's law that we will discuss later. Now coming to Coulomb. The Coulomb is the usual unit that is expressed in quantity of electricity. So it is the unit of quantity of electricity, that is Coulomb. And here it is the definition of 1 Coulomb. 1 Coulomb corresponds to a constant current of 1 ampere for 1 second. Now coming to Faraday. So Faraday, that is abbreviated as F, that is the quantity of electricity associated with one equivalent of chemical change of electrochemical process, that is called 1 Faraday. And again we know that 1 Faraday equals to 96,500 coulombs. So that is the bigger unit of electricity. So here the value of 1 Faraday equals to 96,500 coulombs. And the next one is Siemens, that is S. This is the unit of electrical conductance. So it is ampere by volt. Now coming to the basic laws of electrochemistry. The first one is Ohm's law. So Ohm's law, we know that it is the mathematical relationship between the fundamental electrical quantities. So it is the Ohm's law will show the relationship between EMF E in volt, current length L in amperes, resistance R in ohms, and the expression is I equals to E by R or E equals to IR. Now coming to Faraday's law. So the Faraday's law states that the quantity of current in coulombs associated with an electron transfer process, and that is directly proportional to number of equivalent of substance deposited or liberated in any chemical change at the electrode. Again, I am repeating the statement of the Faraday's law. The law states that the quantity of current in coulomb associated with an electron transfer process, that means the quantity of current is directly proportional to number of equivalent of substances liberated or deposited at the electrode in any type of chemical change. So here the number of equivalent is the number of moles divided by number of electron taking place. So that is called number of gram equivalent. That means Q is directly proportional to number of equivalents. So this is the mathematical statement of Faraday's law, or Q equals to some constant F into number of equivalents. And similarly, Q equals to F into number of moles divided by N. Number of gram equivalent means moles by valency or moles by N. So here F is the Faraday constant, that is equals to 96,500 coulomb, that we have already discussed, and N is the number of electrons taking part in the electrical transformation of the reactions. For example, here such as corresponding general reaction for the reduction of N electron transfer. So here O is the oxidant plus number of electrons, that means that will give the reduced product R. Now coming to the electrode potential. So here first we will discuss how electrode potential will be developed. Now consider, so in order to discuss that, we should go through the particular example how the electrode potential develop. How the electrode potential develop. Now consider a metal M that is placed in a solution containing its ion Mn plus. For example, if you take one copper rod, and if one copper electrode is placed in copper sulfate solution, that means the Cu electrode present inside is Cu2 plus ion. So here in general sense, consider a metal M that is placed in a solution containing its ion Mn plus. The metal may be looked upon being composed of metal ions and electrons, because we know that the metal that contains Mn plus, that is called kernels, that is the metal ions, and that contains n number of valence electrons. And both the phases, that is the metal and the solution, contain metal ion Mn plus, but the activity of the Mn plus of the metal will be different from that of the solution, and the distribution of metal ion takes place in the two phases in order to get the position of equilibrium. Here we will consider for the two types of metals. So here suppose this is one copper sulfate solution we have taken, because we know that in the copper sulfate solution Cu2 plus and SO4 2 minus ions are there. So that means the copper sulfate solution will contain Cu2 plus ions. And if in the copper sulfate solution you will dip a copper electrode or copper rod, so the copper rod contains copper atoms, Cu atoms. Now the Cu atoms immersed in Cu2 plus solution. So there will be development of a potential between the Cu and Cu2 plus ion. So here, in order to explain in details, we will consider two types of metals. One is less active, for example copper, and the other one is more active, for example zinc, and placing them in contact with their salt solution. The first one, in the first case, copper is in the first case, a piece of copper metal is placed in a solution of copper sulfate, and some of the copper ions may be deposited on the copper metal, accepting electrons from the metal conduction and bands and leaving the metal with a small positive charge, and hence the solution with a small negative charge. So here, so this is the copper electrode immersed in a solution of or placed in a solution of copper sulfate solution, and we know that the copper metal contains Cu2 plus ions and number of valence electrons, and the Cu2 plus ion will be deposited on the Cu2 plus ion from the solution that will be deposited on the copper electrode, so that the electrode will become somewhat positively charged. A small positive charge will be developed on the surface of the electrode. And in the second situation, which is more active metal, it will be the other way around. A few metal ions from the metal surface may be passed into the solution, because this is one active metal. So few metal ions will pass to the solution. So here in the second case, the zinc electrode is dipped in zinc sulfate solution, and the zinc electrode or the zinc metal contains Zn atoms, As these are more active atoms, so they will go to the solution in form of Zn2 plus, leaving two electrons on its surface. So the electrode surface will become negatively charged. So giving the metal a small negatively charge and the solution of a small positive charge. In both the two cases, the positive and negative charges will be located at the surface of the metal solution phase, that is the interface. So as a result, a electrical double layer is established with corresponding to the potential difference between the metal and the solution. This is called electrode potential. So that means here we have discussed about the two different types of metal electrodes dissolved in their corresponding salt solutions. So the first one is copper metal dissolved in copper sulfate solution, and copper metal is less active metal. So on the copper metal electrode, some of the 2 plus ions, some of the Cu2 plus ions from the solution will be deposited on its surface. So the surface will become slightly positively charged and the solution will become slightly negatively charged. So one electrical double layer will be formed. So the surface of the electrode will be positively charged and its surrounding will become negatively charged from the solution side, and hence a potential will be developed. Similarly, in case of the more active zinc metal, if one zinc electrode will be dissolved on the zinc sulfate solution, and as the zinc metal is more reactive, some of the zinc atoms from the surface of the zinc metal will go into the solution in the form of Zn2 plus, leaving two electrons on its surface. So the surface of the zinc metal will become negatively charged and the solution will become positively charged, and hence potential also develop in this case, and that is called electrode potential. Now coming to measurement of electrode potential. So the direct measurement of potential difference between the electrode and the solution is not possible, but it can be measured with respect to an arbitrarily defined reference electrode. So directly we cannot measure the potential difference between the electrode and the solution, but it can be measured in one indirect method. That means by choosing one reference electrode. Such a reference electrode was first proposed by Nern, and that is known as standard hydrogen electrode, or that is in the short form that is called SHE. So if we connect the half shell means if we connect the electrode containing the solution with SHE. SHE means standard hydrogen electrode. Then the potential difference of the cell is the electrode potential of that electrode. Is the electrode potential of that electrode solution half shell, because arbitrarily it is considered that the potential of SHE is considered to be zero. So by universal agreement among the chemist and the standard hydrogen electrode was chosen as the reference electrode. Thus, the electrode whose potential is to be measured, thus the electrode whose potential is to be measured is coupled with a SHE or standard hydrogen electrode, and the EMF of the resulting cell is the electrode potential and the electrode being studied. So by this method, the electrode potential can be measured. Now coming to, so this is the method by which the electrode potential can be measured. So after that, we'll discuss the LJP, or that is called liquid junction potential. So here, when two different electrolyte solutions are brought into contact, an electrical potential difference arises at the zone of contact. This potential difference is termed as liquid junction potential or diffusion potential, that is called EJ. So it is called due to the diffusion of one ion from one region to another region. That means it is due to the diffusion of ions from the higher concentration region to the lower concentration region, depending upon the concentration gradient. So, and the individual mobility of each ion, various types of liquid junction potentials are possible. So, here we will discuss a particular example of the LJP or liquid junction potential. Suppose we could prepare a quiet interface between the two solutions containing the same electrolyte but with different concentration. For example, the first compartment that contains 0.1 m HCl and the second one is 0.01 m HCl. So if we join the two different solutions, that is the first one is 0.1 m HCl and the second one is 0.01 m HCl. On making contact of these two solutions, both the H plus and Cl minus ions will diffuse from the left to right immediately. So here one porous division is there. So here it is this is the liquid so this is the diagram of the LJP or liquid junction potential. You can see. So here one porous partition or porous division is there. The left hand side of the solution contains 0.1 m HCl. The right hand side contains 0.01 m HCl, and here you can see both the H plus and Cl minus ions will move from the left to right, because the left one is high concentration region and the right one is low concentration region. So due to the concentration gradient, both the H plus and Cl minus ions will diffuse immediately from left to right. However, the hydrogen ions move much more rapidly than the Cl minus ions, because the transport so here the H plus ions will diffuse much more rapidly than that of the Cl minus ions, that is indicated by longer arrow. You can see, so this is the H plus ions and the Cl minus ions. Both the ions are diffusing from the highly concentrated region to the low concentration region through the porous division, but the H plus ions are diffusing at a more rate as comparable to the Cl minus ion, that is shown by larger arrow for H plus ions and smaller arrow for Cl minus ions. Thus, the H plus outturns Cl minus ions, and there is a slight tendency for a chance of separation with the right side of the junction acquiring a positive charge and thereafter the left side acquiring a negative charge. So, as the rate of diffusion of the H plus ion from left to right is greater than the rate of diffusion of Cl minus ion from left to right, so the left hand side will become comparatively more negatively charged, while the right hand side will become comparatively more positively charged, and hence thus a slight tendency for a charge separation with the right side of the junction acquiring a positive charge and the left side acquiring a negative charge, and a slight separation of charge will be developed. Thus, the liquid junction potential may vary over a considerable range depending upon the condition of the cells. This potential can be minimized by using a salt bridge containing concentrated electrolyte solution of cation and anion having comparable mobility. For example, potassium and chloride ions have comparable mobility, and the salt bridge of saturated aqueous potassium chloride and agar gel are widely used to minimize the liquid junction potential problem. Now coming to the different types of electrochemical cells. We know that the electrochemical cells consist of two metallic electrodes that is immersed either in the same electrolyte solution or two different solutions that are in electrolyte contact. The electrochemical cell can operate to convert chemical energy into electrical energy and vice versa, depending on whether the cell reaction is spontaneous or non-spontaneous. The cell in which the electrode reactions occur spontaneously when the electrodes are extremely are when the electrodes are externally conducted by the conductor, it serves as the means of converting chemical energy into electrical energy, that is called galvanic cell or voltaic cell. That means the meaning of the galvanic cell or voltaic cell is that type of cell that will produce that will convert chemical energy into electrical energy due to different types of chemical reaction takes place, and due to different types of spontaneously chemical reaction, the chemical energy will change into electrical energy. That type of electrochemical cell is called galvanic cell or voltaic cell. And another type of cell is there, the cell in which the cell reaction is forced to occur, that is in non-spontaneous direction or non-spontaneous manner, by passing the current through the cell from an external source to affect a chemical transformation, that is called electrolytic cell. So that means in the voltaic cell or galvanic cell, chemical electrical energy will be produced due to chemical reaction, and that is one spontaneous process, that is in the galvanic cell or voltaic cell. And in second type of cell, that is called electrolytic cell, in which the externally you have to supply electrical energy, and due to that type of electrical energy, chemical reaction will take place inside the cell, that is called electrolytic cell. So here first we will discuss the galvanic cell. So galvanic cell means there is a conversion of chemical energy into electrical energy due to the chemical reaction takes place inside the cell. So in a galvanic cell, the system comprises of two electrodes. Two electrode means two half cells. So you can see in the figure, this is one half cell and this is another half cell. And when both the cells are connected through external conductor and a salt bridge, that is called a complete cell or galvanic cell. And here many types of galvanic cells are there, and particularly we will discuss a Daniell cell. A Daniell cell in which zinc electrode is immersed in zinc sulfate solution and copper electrode is immersed in copper sulfate solution, and that is connected through salt bridge and conducting wire externally, that is called galvanic cell. That is called a Daniell cell. That means Daniell cell is one type of galvanic cell, and many other galvanic cells are also there. So in a galvanic cell, the system comprised of two electrodes or two half cells that processes occur whereby energy associated with chemical reactions is converted into electrical energy. In this way, we can obtain a useful system upon which a meaningful measurement can be performed on such cell, that is called Daniell cell. So here, so this is the diagram of a Daniell cell. Daniell cell is one example of galvanic cell. You can see. So in the Daniell cell, what is happening? You see in the left hand side electrode, zinc electrode is dipped in zinc sulfate solution, and in the right hand side half cell, copper electrode dipped in copper sulfate solution, and both the electrodes are connected through wire externally, and also both the electrodes are connected through salt bridge, the salt bridge that contains saturated KCl solution, and so the salt bridge is one type of U-shaped tube where the both ends contains the porous disc. So the solution of the two half cells are connected with a salt bridge, say an inverted U tube containing a solution of potassium chloride inside agar gel. So the zinc strip or the zinc electrode immersed in zinc sulfate constituting zinc electrode, that is one half cell. Similarly, one copper strip immersed in copper sulfate solution that constitutes the copper electrode. This is the second half cell. On combination of these two half cells, that will give the complete cell. Such a cell was invented by L. Galvani, that's why that is called galvanic cell. It were many of the such type of cells developed by supply of electrical energy before electrical generators were available. So here you can see the cell reactions are oxidation and reduction. So reactions are taking place in the complete cell, and here are the copper electrode. Copper ions are reduced where the electrons are consumed, and that is known as cathode. And in the zinc electrode, the electrons must be supplied, which is done by the oxidation of zinc Zn0 to Zn2 plus, that is called anode. Now again we move to the diagram. Already we have discussed that zinc is more active metal than that of the copper, and you see the left hand side electrode. What is happening when zinc rod is immersed in zinc sulfate solution? Then the zinc atoms from the zinc rod or zinc metal will ionize to Zn, from Zn atom to Zn2 plus ion, and they will, and that will go to the solution. So that means zinc atoms ionize to Zn2 plus ion, and Zn2 plus ion go to the solution, and the two electrons which are present on the surface of the zinc metal, that will transfer through the external wire in this direction. You can see, so this is the direction of the electrons transforming. That means electrons are generated from the zinc electrode or zinc half shell, and similarly move to the second half shell, that is the copper electrode in the second half shell. So you can see the electrons are coming from the zinc half shell through the voltmeter, and so when that will reach on the surface of the copper electrode, then immediately copper 2 plus ion, Cu2 plus ion from the solution, Cu2 plus ion from the solution will go to the surface of the copper electrode, and they will consume the electron which is supplied by the left hand half shell, and they will convert it into copper 2 plus to copper 0 or atomic copper, and that will deposited on the copper electrode. And if this reaction will continue for some time, you will observe that the mass of the zinc electrode will gradually decrease, while the mass of the copper electrode will gradually increase. And overall what is happening inside the left half shell, inside the left half shell, the concentration of Zn2 plus ions will increase. So in order to balance that, the Cl minus ions from the salt bridge will liberated to the left hand half shell. And similarly in the right hand side, the concentration of SO4 2 minus ion will increase, because Cu2 plus ions from the solution will deposit on the surface of the copper, and they will absorb two electrons to form copper metal. So in the solution, copper 2 plus, the concentration of copper 2 plus ion decrease. Now in order to electrical balance, K plus ion from the salt bridge will liberated to the solution. Now when the circuit is closed, the cell operates spontaneously, and the copper has a high positive potential than that of the zinc, and the electron flow from the zinc to the copper through the outer circuit, in the outer circuit through the wire, and the flow of electron is called electric current. And so here you can see the electron will flow from left to right in this direction, and hence electric current will move from right to left. So conventionally the flow of current is considered to be as a direction opposite to the direction of flow of electron. Based on this consideration, based on the consideration of potential, such that the region of more positive potential or to the less positive potential. And here the cell reaction where the zinc is reduced, where the zinc Zn metal or Zn0 is oxidized to Zn2 plus by liberation of two electrons, and hence the left hand side electrode will become negatively charged. So the left hand side electrode or the zinc electrode is called anode, where at zinc electrode electron must be supplied, which is done by the oxidation of zinc to Zn2 plus, and this electrode is called anode. And similarly the right hand side electrode where the copper, that is the copper electrode, where the copper ions are reduced, the copper ions from the copper sulfate solution are reduced by absorbing two electrons, by consuming two electrons and converted into Cu0 plus, and that is called the cathode. Now, so here will write the cell reaction chemically. So the here will so write the cell reaction in a logical manner following a convention such that anode, that is the negative electrode, is always on the left side, and cathode, that is the positive electrode, is always on the right side. The logic in writing in this way that the chemical reaction taking place in the cell follows the way that occurs in it, and in the more general way it is to say that the left hand side electrode of the cell, that is as written corresponding to the oxidation reaction, that means the left hand side of the cell corresponds to the oxidation reaction where Zn0 is converted into Zn2 plus, that is the reaction supply of electrons from the external source. As oxidation reaction takes place on the left hand side electrode, so electrons will be supplied from that electrode to the external circuit. And similarly, the right hand side electrode corresponds to the reduction reaction, that is the reaction of accepting electron from the external circuit, and here that can be mentioned like this: the left hand side electrode where the Zn is converted into Zn2 plus. So here this is, so Zn is converted into Zn2 plus. So one vertical bar is given between, so that vertical bar corresponds to the potential developed between the Zn and Zn2 plus. So here Zn is converted into Zn2 plus, and this one is the activity or concentration of Zn2 plus inside the solution. And after that one salt bridge is there. So the salt bridge corresponds to two vertical parallel bars. So this is one vertical bar, but the salt bridge corresponds to two vertical parallel bars that indicate the liquid junction potential or the salt bridge. And in the right hand side, what is happening, the electrons coming externally to the right hand side electrode. So here the copper 2 plus ion present in the solution, where the activity of copper 2 plus ion, so here this is the activity of copper 2 plus ion or concentration of copper 2 plus ion. So the copper 2 plus ion from the solution will accept the two electrons coming externally towards this electrode, and they will convert it into copper solid. So overall, the left hand electrode oxidation reaction it takes place, that is the anode, whereas in the right hand side electrode where the reduction reaction takes place, that is called cathode. And here the chemical reactions taking place in the two half cells can be summarized like this: in the left hand side, Zn solid is converted into Zn2 plus aqueous by releasing two electrons, and similarly in the right hand side, copper 2 plus ions from the solution by accepting two electrons converted into copper solid. And if we add the two reactions, the net reaction of the overall reaction can be considered as the summation of the two half reactions that mentioned in 1.4 and 1.5. So if we add the two reactions, the overall reaction will become zinc plus copper 2 plus gives rise to zinc 2 plus copper. And the EMF of the galvanic cell is the difference between the potential of the two electrodes, and the potential difference are the zinc of contact of the two electrolytic solutions. So the latter is usually termed as LJP or liquid junction potential. Thus, there is no liquid junction potential. The EMF of the cell, thus when there is no liquid junction potential, the EMF of the cell is the potential difference between the two electrodes. So here E cell equals to E right minus E left. That means E cell equals to E cathode minus E anode. Here E right is the potential of the right electrode and E left is the potential of the left electrode. By convention, the electrode potential are the reduction potential, therefore negative sign is there in equation 1.8, and so that is compensating the electrode reactions occurring in the reverse direction. Using the same convention, the E cell for the above Daniell cell what we have discussed, so the E cell of the above Daniell cell can be written as E cell equals to E copper 2 plus copper minus E zinc 2 plus zinc. So the E cell, the cell EMF is always positive. The cell therefore written in such a way that E cell is positive. So here some questions are there. So in the first question, write the cell reaction for the galvanic cell presented below. Here we have discussed particularly for the copper zinc cell, or that is called a Daniel cell. But in the question it is given that iron copper cell. So here you have to write the cell reaction. Now coming to the norm equation. So this is one most expected long question for your semester examination. So first one is derivation. So here we will discuss the derivation of Nernst equation. So in order to derive the Nernst equation, first you should remember the first law of thermodynamics. The first law of thermodynamics. So the first law of so this is the mathematical form of first law of thermodynamics, that is del U equals to Q plus W, where del U is the change in internal energy of the system and W is the work done on the system. So that's why negative positive sign convention is there. If work is done by the system, you have to put negative sign. So here positive sign is there. So that's why W is the work done on the system. And consider a reversible process taking place in a system at constant temperature and pressure, in which both the pressure volume work or mechanical work, that is P del V, or electrical work are done, and hence W equals to minus P del V plus W electrical overall work. So we know that for a reversible process at constant temperature, the entropy change del S equals to Q reversible by T, and that is Q equals to T del S. Now substituting the value of Q here, we can write in place of equation 1.10, we can write del U at constant temperature and pressure equals to T del S minus P del V plus W electrical, because here it is the overall work, but we know that the overall work contains both the mechanical work and electrical work. So here the mechanical work is minus P del V, and the electrical work is W electrical. So in place of W, we can write minus P del V plus W electrical. And in place of Q, we can write T del S. So the equation of 1.10, that can be written as del U at constant temperature and pressure equals to T del S minus P del V plus W electrical. And similarly, at constant pressure, the change in enthalpy del H of a system can be given as del H equals to del U plus P del V. And similarly, at constant temperature, the Gibbs free energy change del G, that is given as del G at constant temperature and pressure equals to del H minus T del S. And here del H equals to del U plus P del V. Now, from equation 1.14 and equation 1.15, we can write del G equals to, so that means in place of del H, we can write del U plus P del V. So in place, so if you write del U plus P del V in place of del H, so the equation 1.15 can be converted into del G at constant temperature pressure equals to del U plus P del V minus T del S. So this is equation 1.16. Now from equation 1.13 and equation 1.16, this one 13 and 16, if you compare both the equations, we can write del G at constant temperature and pressure equals to T del S minus P del V plus W electrical plus P del V minus T del S. So this P del B will cancel, T del S will be cancelled. So del G at constant temperature and pressure is only the electrical work. Now, considering the galvanic cell which has two terminal across with a potential difference E, when a charge Q is moved through the external circuit, the work done can be written as W equals to EQ. That means the potential difference into charge. So W equals to EQ. And again we know that Q equals to number of electron transferred through chemical reaction into F. So Q equals to NF, where F is Faraday constant, that is equal to 96,500 coulomb, and that is the charge on 1 mole of electron. So that is calculated in a similar way. So that is the charge of 1 mole of electron, and N is the number of moles of the electrons involved in the cell reaction. So W electrical will become minus NFE. So in place of Q, you can write NF. So W electrical will become minus NFE. This is equation 1.20. Now combining with the equation 1.17, we can write del G equals to minus NFE. Now consider a chemical reaction such that, so this is a reversible chemical reaction, that is AA plus BB gives rise to PP plus RR. So here small a, small b, small p, small r are the coefficients, while the capital A, capital B, capital P and capital R, capital A, capital B are the reactants, and capital P, capital Q, capital P, capital R are the products. So del G of this reaction, that is the free energy, that is given by the equation del G naught plus RT ln concentration of P to the power small p into concentration of R to the power small r divided by concentration of A to the power small a into concentration of B to the power small b. In the other sense, you can tell del G naught plus RT ln activity of P to the power small p into activity of R to the power small r divided by activity of A to the power small a into activity of B to the power small b. Here R is the universal gas constant, T is the temperature in the Kelvin scale, and del G naught is the standard Gibbs free energy change. That means when all the reactant and products in their standard state. So here again we know that del G naught equals to minus NF E naught. So E naught is the standard electrode, standard redox potential. Now putting the value of del G naught from equation 1.27 in equation 1.23, we can write minus NFE equals to minus NFE naught plus RT ln activity of P to the power P into activity of R to the power R divided by activity of A to the power small a into activity of B to the power small b. Now, after dividing both sides by minus NF, so in this equation 1.25, if we divide minus NF both sides, then the equation can be converted into E equals to E naught minus RT by NF, ln activity of P to the power small p into activity of R to the power small r divided by activity of A to the power small a into activity of B to the power small b. Alternatively, it can be written as reactant product with a required charge. So here P are capital P, capital R the products, and capital A, capital B are the reactants. So alternatively, if we will just exchange the denominator and the numerator, the negative sign will be vanished and that will become the positive sign. So this equation 1.26 can be converted into E equals to E naught plus RT by NF ln activity of A to the power small a into activity of B to the power small b. That means reactant will come in the numerator side, and activity of P to the power small p into activity of R to the power small r. So just we are reversing this one, so the negative side will become positive one, and hence And again, this is the ln means natural logarithm. If we convert natural logarithm into logarithm base 10, so the equation can be written as E equals to E naught plus 2.303 RT by NF log base 10 activity of reactants divided by activity of products. So here the term ln, so already that we have discussed. Now substituting the numerical value of universal gas constant R and F, that means 96,500 coulombs, and making the approximation that activities of the concentrations are equal for at room temperature, that means at 25 degrees Celsius, the equation can be written as E equals to E naught plus 0.0591 by N log base 10 concentration of A to the power small a into concentration of B to the power small b divided by concentration of P to the power small p into concentration of R to the power small r. This is the form which is commonly used in nonce equation. To further understand the nonce equation, now we will take few examples. Now consider a simple electrode M where the metal M dissolved in its solution that constitute one half shell, and here the metal cation equilibrium can be written as Mn plus n electron, that is converted into M at 25 degrees Celsius, that means at room temperature. The nonce equation can be written as E equals to E naught plus 0.0591 by N log concentration of Mn plus divided by concentration of solid, but we know that concentration of any solid substance, that is unity. So this equation can be written like this. So here this is the nonce equation, and there is a chance of long question of derivation of nonce equation. If in the semester examination derivation of nonce equation will be there, then you will start from here, derivation of nonce equation up to this one, and after that we are applying the nonce equation for a particular example. And similarly, for a general form of the redox reaction, the nonce equation, suppose the redox reaction is like this: XO plus MW is in equilibrium with YR plus ZZ, where capital O is the oxidized species which are being reduced, and capital R is the reduction product, capital W, capital Z, some of the other species. Small x, small m, small y, small z are the stoichiometric coefficients of the respective species, and the nonce equation for this reaction can be very simply written as E equals to E naught plus 0.0591 divided by N log concentration of O to the power x into concentration of capital W to the power small m divided by concentration of capital R to the power small y into concentration of capital Z to the power small z. So, for the galvanic cell mentioned in the above at 25 degrees Celsius, the nonce equation, galvanic cell means what we have discussed in the Daniel cell, copper zinc cell. So, what we have discussed in the copper zinc cell at 25 degrees Celsius, the nonce equation can be written like this: E cell equals to E naught cell plus 0.0591 divided by 2. So why 2? Because in the chemical reaction you can see 2 electrons are transferred. Now coming to the Daniel cell, what we have discussed here in this overall reaction, 2 electrons are transferred from the zinc metal to the copper 2 plus ion. So the zinc metal will be converted into Zn2 plus, and the copper 2 plus ion will be converted into copper metal. So as 2 electrons are transferred, so in place of N we can write 2. And hence the nonce equation for the above Daniel cell, that can be written as E cell equals to E naught cell plus 0.0591 by 2 log concentration of the reactant log concentration of Cu2 plus divided by concentration of Zn2 plus. It can be applied for evaluating EMF of the cell. Now, your another example is there. Consider the following reaction, that is MnO4 minus plus 8H plus 5 electrons that will form Mn2 plus for 4 water. Here the Nernst equation for this half shell that can be written as EMnO4 minus slash Mn2 plus equals to E naught minus. So here you can see as 5 electrons are transferred, in place of N we are putting 5 minus 0.0591 by 5 log concentration of the product divided by concentration of the reactants. So here negative sign is there. If you put positive sign, the denominator side you will write concentration of the reactant, and in the numerator side you will write the concentration of the reactant, and in the denominator side you will write concentration of the product. So this is about the Nernst equation, and in similar manner you can write the Nernst equation for any type of cell reaction. So here we'll take 2-3 minutes of break. After that again we'll continue. So now we will continue. So here we will discuss the cell potential. So the potential difference between the two electrodes, that means between the two half cells connected properly to form a galvanic cell under the condition where no current flow through the system, is called EMF of the cell or cell potential. It is expressed in the unit of volt. Again, repeating the same thing, the potential difference between the two electrodes or the two half cells connected properly to form a galvanic cell under conditions when no current flows through the system is called EMF of the cell or cell potential. It is expressed in the unit of volt. However, under the condition when an appropriate current flows through the cell, the method of measurement of cell EMF result voltage values lower than the cell potential. This is because the passage of current allows the appropriate reaction to occur, and hence changing the concentration of the solution species and lowering the potential difference between the two electrodes. Also, the ohmic drop due to the flow of the current through the internal resistance of the cell may be lower the voltage, and providing measured potential will be less. So here, so the cell potential of a system can also be calculated on theoretical basis using the Nernst equation. So these calculation can be done in two ways. In one way, we calculate the potential of the individual electrode using Nernst equation, that is each half cell involves separate reaction which is considered in isolation, and the higher value of the reduction potential, that is more positive value or less negative value of the potential of the electrode, indicates that it will act as the cathode. That means the where the reduction potential value will be more positive or less negative, that can be act as cathode, and that can be written in the right hand side, whereas the less positive value or more negative value, the half cell in which the electrode potential will be less positive value, electrode potential means the reduction potential will be less positive value or more negative value, that is having the lower value of potential, and that indicates that it will act as the anode and will be written on the left hand side. Now, the cell potential is the difference between the two electrode potentials, and hence E cell equals to E right minus E left. In the other way, we calculate E cell in a consolidated manner by first calculating the E naught cell value of the standard potential, that is E naught cell equals to E naught right minus E naught left. So here a particular example is there. You can see a cell is set up as follows. Here zinc Zn2 plus, so the concentration of Zn2 plus is 5 into 10 to the power minus 3 mole, that is molar concentration. And copper 2 plus copper, here the concentration of copper 2 plus is 2 into 10 to the power minus 2, and the standard electrode potential E naught values are given. And here the question is calculate the cell potential. So this type of question definitely that will come in the semester examination. Calculate the cell potential and indicate the polarity of the electrode. That means you have to write which one will be placed in the right and which one will be placed in the left, and which one is cathode and which one is anode, and direct the spontaneous reaction. So the cell diagram specifies that the overall cell process involves oxidation of zinc to Zn2 plus and reduction of copper 2 plus to copper metal. From this information we can see there is a oxidation of zinc to zinc 2 plus and reduction of copper 2 plus to copper metal. So the electrode reactions can be written as Zn2 plus 2 electron, that will give rise to zinc metal or zinc 0. Similarly, copper 2 plus 2 electrode can be mentioned as copper 0. So here in both the cases the reduction potentials are given. So in both the cases the reduction potential can be, the standard reduction potentials are given. So here E naught equals to minus 0.763, and in case of copper E naught equal, in case of copper half cell E naught equals to plus 0.337 volt, and hence the individual electrode potential can be calculated using the Nernst equation. So first we will calculate copper half cell, the electrode potential of copper half cell. So E copper 2 plus copper equals to E naught plus 0.0591 divided by 2 because 2 electrons are transferred log concentration of copper 2 plus. So that is 0.337. It is given the standard reduction potential of the copper half cell that is given in the question plus 0.0591 by 2 log concentration of copper 2 plus that is given in the question. By solving this one, we can write the electron potential of the copper half cell is 0.287 volt. In similar manner, the electrode potential of the zinc half cell that can be calculated as minus 0.831. So it is apparent that the copper half cell has a higher reduction potential, hence it will act as the cathode, and similarly the zinc half cell having lower electrode potential that is acts as anode. So that the interlinked cell reaction can be written like this: copper 2 plus by absorbing 2 electron converted into copper metal, while zinc metal releases 2 electron and converted into copper 2 plus, and the overall cell reaction can be written as zinc plus copper 2 plus gives rise to zinc 2 plus plus copper, and the voltage difference between the electrode E cell equals to E right minus E left, that is E copper half cell minus E zinc half cell. Already we have calculated the value of the electrode potential of the copper half cell is 0.287, and the value of the electrode potential of the zinc half cell that is minus 0.831. So E cell equals to 0.287 minus of minus 0.831, and overall that will become 1.118 volt. And in alternative manner, we can directly apply the Nernst equation: E cell equals to E naught cell plus 0.0591 by 2 log concentration of the product divided by concentration of the reactant. So here E naught cell can be written as E naught copper half cell minus E naught zinc half cell. These values are given in the question, and by putting the concentration values, same result will be obtained. Now coming to classification and an overview of electroanalytical methods. So here we will discuss the different. So up to these are the fundamentals of electrochemistry, and after that Now up to this, we have discussed the fundamentals of the electrochemistry, and these fundamentals will be applied in the various electroanalytical methods. The first one will discuss the potentiometry. So this technique involves the measurement of potential at zero current flow. Again, potentiometry, this technique involves the measurement of potential at zero current flow. The analytical use of this technique is made in two ways, that is known as direct potentiometry. In this technique, we utilize the single measurement of potential, and the Nernst equation is used to relate the cell potential to the concentration of the analyte. And the liquid junction potential and the activity coefficients influence of the various of the value of the cell potential. In the second technique, that is known as potentiometric titration. So the first technique is direct potentiometry, and the second technique is potentiometric titration. The potentiometric titration, a set measured potential is used to detect the change in the concentration that occurs at the equivalent point of a titration. In these titration, the change in the potential is of importance, and thus the influence of junction potential and the activity coefficient may be ignored. So here these are the two different long questions. The first one is direct potentiometry and the second one is potentiometric titration. So these are two different 5-mark questions. So you see here this is first we'll discuss the direct potentiometry. In the direct potentiometry, we measure a potential difference between the two electrodes immersed in a solution and connecting the cell so form to a voltage measuring devices. That is called a potentiometer, vacuum tube, voltmeter, etc. The cell formed by the two electrodes or the two half cells and the solution is known as electrochemical cell, that is called galvanic cell. The net reaction can be considered as the sum of the two half cell reactions in which each half cell reaction is the representation of the actual chemical process that occurs in the individual electrode of the galvanic cell. So the half cell reaction always include the electron transfer. Usually, one of the electrode is chosen in such that its potential is invariant and that is termed as the reference electrode. The potential of the other electrode is the function of the concentration, that is more correctly activity. So activity is similar to concentration of the species involved in the electron transfer process through the Nernst equation. So this electrode is termed as the indicator electrode. That means in the direct potentiometry method, two half cells are connected to form the potentiometer. Here, one half cell that will act as the reference electrode, and the other half cell that will act as indicator electrode. And under this condition, E cell equals to E indicator minus E reference plus liquid junction potential. So E cell is the EMF of the galvanic cell, E indicator is the half cell potential of the indicator electrode, E reference is the half cell potential of the reference electrode, and EJ is the liquid junction potential developed at the interface between the two electrolytes. So here, the concentration of the solution is determined by single measurement of the cell potential by applying Nernst equation or from calibration curve that is drawn by taking E cell versus logarithm of the concentration of the species, and from this potential measured of the series of solution known concentrations. It is important that the indicator electrode should respond selectively to the species of the analytical significance of this practical instrument. So this is the setup. So when if a direct potential method will be there, you have to discuss, you have to write up to this. So this is up to this portion you have to write. Now coming to the potentiometric titration. So this one is the second one, and that is the most common application of potentiometry, the potentiometric titration. So in this titration, the potential between appropriate indicator and reference electrode is immersed in the sample is mentioned during the titration. So the titration can be performed manually or with an automatic titration equipment. The cell potential is plotted as a function of the volume of titrant. And let us consider the redox titration that can be represented as R1 plus O2 gives rise to O1 plus R2. Here R and O stand for the reduced and oxidized species. The potential of such system depends upon the ratio of concentration of oxidized species by concentration of the reduced species. So in the above equation 1.43 is the stoichiometry. We can plot the cell potential against the volume of the titrant, and since the potential of the reference electrode remains constant, the variation of the potential of the indicator electrode are followed during the titration, and endpoint is determined from the resulting titration value. The indicator electrode should be in such that it responds the component used in the titration. The amount of the reactant is calculated from the volume of the titrant that required to reach the equivalent point. The equivalent point is detected by an abrupt change in potential and can be determined by any one of the following method, that is the tangential method or the first derivative method or the second derivative method, and the details that we will discuss in unit 2 and 3. Now coming to the voltammetry. So in the voltammetry method, in voltammetry, an electroactive species is consumed that may be oxidized or reduced species, and the electroactive species is consumed at the surface layer of the indicator electrode of the electrolytic cell, and the resulting current due to the electron transfer process is measured as a function of applied potential. Such electrolysis is carried out under controlled condition of diffusion and or convention. In diffusion layer electrolysis method, only thin layer of the solution immediately adjacent to the electrode undergoes electrolysis. In this method, electrical variable is related to the concentration of the bulk, or usually the time of the electrolysis is short as the only negligible fraction of the reactant is electrolyzed and the reactant concentration of the bulk solution is not altered. In voltammetry, we study the relationship between the current and the electrode potential and their application in chemical analysis. The current potential characteristics studied commonly by the arrangement of the figure 1, in which the voltage applied to the cell C is adjusted by means of the potentiometer P and the current through the cell is read through the galvanometer G. So this is the circuit diagram of the current potential characteristics. And after that, polarography. So here, out of the various type of electrode used in the voltammetric technique, one of the electrode is dropping mercury electrode, that is called a DME, is particularly useful and corresponding to the corresponding voltammetric method is known as polarography. So the use of DME in the chemical analysis, the DME is essentially composed of a capillary connected by mercury reservoir. The bore of the capillary, the length of the capillary and the head of the mercury is adjusted in such a way that a drop is dislodged every 2 to 6 seconds. A platinum wire is immersed in the mercury reservoir and the DME is coupled with the unpolarized electrode. The polarography consists of electrolyzing a solution of the electroactive substance between a DME and some reference electrode, that is acts as anode. The area of the anode is large correspondingly, so that it may be regarded as unpolarized and the potential of the such electrode remain fairly constant. So here this is the circuit diagram of the manual polarographic circuit. Here you can see, so that is the saturated calomel electrode is there, and this is the capillary right method, and this is the DME. So in the DME, one platinum wire is immersed, and hence on applying potential between the two electrodes and increasing its value in a stepwise manner, the following processes takes place. First, only a small current flows, so that is called the residual current. This continue until the decomposition of the potential reducible ionic species is reached. At the end point, the following reaction will take place. That is, the Mn plus will consume n number of electrons to form the metal, and here the metal is the reducible metal. After a steep rise in the current is observed and will continue to rise the increasing potential till the current reaches a limiting value. So this is the I versus E current for the polarogram. So here this is the x-axis, the y-axis corresponds to the current in microampere, and the y-axis is the applied voltage. So the conditions are set such that the diffusion is main process and of the mass transfer. This can be done by minimizing the convection and migration process. The limiting current under this condition is known as diffusion current, or that is called ID. So the factors affecting the diffusing current are examined by D, that is called Ikovic, and is examined by D. Ikovic, and he gave the following equation: ID equals to 708 n into m to the power 2 by 3 d half t to the power 1 by 6 c. So here ID is the diffusing current, n is the number of electrons consumed in the reduction process of Mn plus, and D is the diffusing coefficient, M is the rate flow of the mercury, T is the time, and C is the concentration of the Mn plus, and 708 is the combination of the constant and conversion factors involved changing in the unit taking into account. So this equation 1.44 gives a direct relationship between ID and concentration. Hence, ID is directly proportional to C, or ID equals to some constant K into C. So here K can be evaluated by noting the current with standard solution of the substance of interest. And the next one is the amperometry. So in polarography, we have seen, so that in particular polargram of limiting current, just wait for 1 minute. Yes, we will continue now. So here, after that we will discuss amperometry. So the amperometric titration are more accurate than the voltammetric methods. Further, this titration can be performed even when the substance being determined is not reactive, since an equally satisfactory equivalent point can be located with either of a reactive titrant or when the product is reactive. modification had been used in the amperemetric indicator. On plotting a data for current versus volume of titrant, we get straight lines having the different slope. The equivalent point is obtained by extrapolating the linear segment of their intersection. The microelectrode may be a DME electrode or solid state platinum electrode or rotating platinum electrode, or that may be an electrode of any other inert material. Now coming to electrogravimetry and coulometry. First one is electrogravimetry. So it is the oldest technique and that was well established by the 19th century. It involved so in the electrogravimetry the method involves the control potential reduction of a solution of a metal salt which is continued till the current falls near to zero. So, thus, the electrolysis is used as a means of chemical transformation, that is the reduction of metal ions, and the product of analysis is weighed as a deposit. That means so the product of the analysis deposited or liberated, that will be weighed as a deposit on one of the electrode, that is called the working electrode. So the increase in the weight of the previously weighed working electrode leads to the determination of the metal content of the sample solution, since the reaction product after the electrolysis is determined ordinarily by weighing, hence the name is electrogravimetry. Now coming to the next one is coulometry. So in primary coulometric analysis, the substance being determined may directly undergo reaction at one of the electrode, and in secondary coulometric analysis, the substance being determined may react with the solution with another substance which generate one electrode reaction. Further, the coulometric analysis, which is considered a reaction proceeding with 100% current efficiency, so that the quantity of the species reacted can be evaluated via Faraday's law. And according to Faraday's law, a given quantity of a chemical change caused by the electrolysis is directly proportional to amount of electricity passed through the cell. That is, if O plus n number of electrons, that will give rise to R, where n is the number of electrons involved in this reaction and O is the reactant to be reduced and R is the reduced product, then according to the Faraday's law, Na equals to the number of moles of the analyte, that is Na equals to Q by Nf. So here N equals to number of moles of the electrons in the analyte half reaction, and F is nothing but that is 1 Faraday, that is the quantity of charge corresponding to 1 mole of the electron, that is 96,500 coulomb, and Q is the quantity of electricity consumed in coulomb. So the value of Q can be determined as a constant current I ampere operate for t second, that is Q equals to IT. And for a variable current, if the current will be constant, that is I ampere, the value of Q can be determined Q equals to IT. But for variable current, Q can be determined Q equals to integration of I dt from 0 to t. Now, the coulometry can be classified into two types, that is potentiostatic coulometry and amperostatic coulometry. So the coulometry can be classified into two types, that is potentiostatic coulometry and amperostatic coulometry. The first one is potentiostatic coulometry. In the potentiostatic coulometry, that is the coulometry technique at constant potential. That's why the name is potentiostatic coulometry. So here in this method, the working electrode is maintained at constant level so that only analyte get quantitatively oxidized or reduced, and there is no involvement of the less reactive species will be there. Here the current is initially high but decreases exponentially when the time will pass and approaches zero at a time so required to attain a reaction product that is qualitatively complete. And Q may be evaluated by the current time integration, that is graphically Q equals to integration from 0 to t of IDT. So here this is the current time relationship of amperostatic coulometry. And after that, potentiostatic coulometry. And after that, the amperostatic coulometry, that is the constant current coulometry. So the constant current coulometry, so the Q is proportional to I, that is Q equals to IT, and that can be directly. So in this titration, the titrant is generally one of the electrode, and the reaction may be taking place directly in the same electrode or with the other electrode. To remove the interference, the reagent is separated from the solution by use single sinter glass. And after that, the next method, that is the conductometry method. So today we will stop here, and from tomorrow we will move from this method. And when the unit 1 will be completed, so here unit 1 is the total discussion of the overall discussion of the paper, and after that from unit 2 again we will discuss in details of the various electroanalytical methods. So that will continue from tomorrow.